Hey Dr. Bell, I bet you're wondering how my hair looks so cool. Well, it all happened in stages. Hey, kind of like the stages of evolution that stars go through. I guess you could call that. The first stage of stellar evolution is kind of like my hair right now. It's messy, with very little resemblance to the finished product. The first four stages of a star are when the star is still mostly just interstellar gas, with nothing but gravity to keep it together, eventually making all the gas get closer and closer together until it eventually becomes a star. Now that my hair is settled, but not quite done, let's talk about a similar phase in the lifetime of a star. As a newborn star condenses and rotates, its temperature increases rapidly, eventually beginning to start nuclear reactions within its core. The star is now stabilized and is able to live out about 90% of its life within the main sequence, depending on the star's mass, before moving into the more volatile and unpredictable death that many stars face. The way that a star is fueled is by converting hydrogen to helium via nuclear reactions. But a star only has a limited amount of hydrogen, so once it is burned up, helium is burned in order to fuel the star. This process repeats, creating heavier and more stable elements until iron-60 is created, the most stable element in the known universe. While the core is doing this, the star itself is increasing in both size and luminosity, becoming a red giant. Eventually, the core ignites, forming a helium shell that turns into a hydrogen-burning shell. What happens next depends on the size of the star. Let's begin with the fate of smaller stars. First off, smaller stars live much longer than larger stars, with small stars being able to live into the tens of billions of years old. But after it has burnt up all its hydrogen and helium, the core contracts, and, while increasing in temperature, it is still unable to reignite nuclear reactions. However, with the two shells burning hydrogen and helium out of sync, it causes pulses in energy, and an easy determinant of a small star about to collapse. Large stars are met with violent deaths as well. As the core burns through to iron, the mass of the star is too great for electron degeneracy pressure to provide a counterbalance, and the star collapses under its own gravity. If the star is greater than about 3 times the mass of our Sun, the neutrons are unable to hold it up. The core collapses into a singularity, forming a stellar black hole. If the star is less than about 3 times the mass of our Sun, then it will be halted by neutron pressure. The shock waves from the sudden halting of movement scatters gas and dust through the nearby space in a supernova explosion. Medium-sized stars share a different fate. Only their cores are unable to burn down to iron-60, instead just increasing in temperature, causing the star to swell to a white dwarf. After the star becomes a white dwarf and the core is no longer sustainable, the core cools and forms a planetary nebula. The core continues to contract until electron degeneracy pressure occurs. This is when many electrons are released with high energy. Such high energy that they begin to speed up to the point where they're able to hold up the collapsing star. The star is now a white dwarf. The pulses of energy slowly strip away the outer layers of the star, until only the core remains. The core continues spinning rapidly and is now a planetary nebula, where it will remain for the rest of its life. The leftover particles from many stars that do not become black holes distribute light and information about the star and its life into the far reaches of the galaxy, and may eventually be reborn a star once again, allowing stars to be both replaceable and sustainable.